So let's do some deep diving into HDFS, the Hadoop Distributed File System. This is basically the underpinning of Hadoop, what actually allows your big data to be stored across an entire cluster in a distributed manner, in a reliable manner, and allows your applications that analyze that data to access that data quickly and reliably. So what's HDFS all about? What's it do? Well, it's really made for handling large files. I mean, yeah, it can handle small files, but really it's optimized for handling very large files that can be distributed and broken up across an entire cluster. And if you're dealing with big data, these might be big logs of information from sensors or web servers or what have you, but it can handle it. And it does this by breaking up those files into blocks. And those blocks are actually pretty large. It's 128 megabytes by default. So, we are talking about big files here. And if it's less than that, then it will just go to one block. But by splitting up these large files into blocks, we're not limited by the drive limitations of a single hard drive, right? We can actually store files that are even bigger than what an individual hard drive can store. So that's pretty cool. The other cool thing is that it allows you to distribute the processing of one of these large files. So if we split that large file up across several different computers, that means different computers can access different parts of that data and process it in parallel. And we can also do things like making sure that the computers that are processing a given chunk of data, a given block of that data, are physically close to where that block is stored, so it can access it more efficiently. So, like I said, those blocks can be stored across several commodity computers, and it doesn't just store one copy of each block. In order to handle failure, it will actually store more than one copy of each block, and so that way, if one of these individual computers goes down, HDFS can deal with that and actually start retrieving information from a different computer that had a backup copy of that block. And it can do this in a clever way such that if a single node goes down, you don't actually lose any blocks from any given file because there'll be another block stored somewhere else at all times. And that's the power of HDFS. The key point here is that it allows you to purchase commodity computers. You don't have to get any special purpose expensive computers that have high availability, because as the side effect of this architecture is that if a single computer goes down, it's not a big deal. We can just fail over to another node that has a copy of that block somewhere else. Let's talk about how HDFS architecture works in a little bit more depth here. So the way it works is there's a single name node, and this name node is what keeps track of where all those blocks live. So basically it's maintaining a big old table of a given file name under some directory structure, virtual directory structure in HDFS, and it knows where to go to actually find every copy of every block that's associated with that file. All right, so it's also maintaining what's called an edit log that maintains a record of what's being created, what's being modified, what's being stored, so that it can keep track of where everything is as things get moved around or new files get created. So that name node is what keeps track of what's on all the data nodes. And individual data nodes are ultimately what your client application will be talking to once it queries the name node to figure out where to go to for given bits of information. And the data nodes are what actually store each block of each file, and they actually talk to each other as well to maintain those copies and replication of those blocks. So let's take a closer look at the example of reading a file in HDFS. So let's say you have an application running on some client node that needs to access data stored on the Hadoop distributed file system. First thing it will do is talk to the name node and say, hey, I want to get at this file. And the name node will come back and say, okay, your file lives on these blocks on these data nodes. And then your client application will know, okay, I need to go back to data node 1 and data node 3 to retrieve the blocks that I need for this particular file. Now, your application won't actually be dealing with it at that level. There are client libraries that will be used. So, your API is just going to be, I want to read these bytes from these files. And under the hood, your HDFS client library will actually figure out, okay, what blocks do I actually need to retrieve? How do I go get them? Your application won't be dealing with those details. That's all happening under the hood. But architecturally, the point is your client node first talks to the name node to figure out where that file is stored, which blocks are on which data nodes, and which ones are the most efficient data nodes for you to reach from your client. And it will then direct your client node to go retrieve data directly from those data nodes that it wants. What if we're writing a file? It's a little bit more complicated. So let's say my client application wants to create a new file in HDFS. Well, first it's going to tell the name node to get about it again, because that name node needs to keep track of, okay, I have this new entry of a new file name and I need to keep track of its blocks. And the name node will come back and say, okay, I created a new entry for you, go create it. And your client node will then say, okay, Mr. Data Node, talk to a single data node and say, here's my data, here's my file. And your data nodes will then talk to each other to actually replicate those blocks across multiple nodes. So that information from the name node comes back through the client node down to the data nodes, where the data nodes then talk to each other. And once that data is stored, it sends back an acknowledgement saying, okay, everything's good. I actually stored that data, and it will send that back through the client node and finally back to the name node once it knows that all the different replicated blocks have been written for that new file. And at that point, the name node will record the fact that this new file exists and it is stored in a replicated manner across the data nodes that it directed it to be stored on. So, it's a little bit complicated. Let's talk about that one more time. So again, writing a file first talks to the name node. Name node says, okay, we're going to create a new file on these data nodes. Client node talks to that first data node, and the data node says, okay, I'm going to store this block. That block's going to be replicated on this data node, and then we're going to pass it on to this data node. And finally, when all the data nodes that we want to replicate that file have written the data successfully, acknowledgements get sent back through and back up to the client node, and finally back to the name node, where it can then record the fact that that file has been written successfully. And now future requests to read that file can be served. So you may be wondering, wait a minute, we only have a single name node. What happens if that name node bursts into flames and melts into a gooey puddle of silicon and plastic and, oh God, that smells bad, right? Well, you may think there's a single point of failure going on here, but there are ways of dealing with that. It is important that only one name node is active at a given time, otherwise clients might not agree on where different blocks are stored, and that'd be bad, right? So there's many ways of dealing with this problem. So kind of the simplest way to do it is to back up your metadata constantly. So one configuration you might have is your name node might be writing out its edit logs both to its local disk and also to some NFS mount that's talking to some backup data storage, maybe even a different rack or even a different data center. And that way, if your name node dies, you can at least restore the edit log from that NFS backup. So when you bring up a new name node, you can actually sort of bootstrap it using an edit log that you already had. Now, there will be some lag between actually writing out that backup data, so you will lose some information, but at least you'll have something to start from if that happens. So if you can tolerate some downtime in the event of a name node failure, that's probably the simplest way to deal with it. You can also run secondary name nodes, and it's not actually what it sounds like. You're not running an actual second name node at the same time. It's not a hot backup. All it's doing is maintaining a merged copy of the edit log from your primary name node. So it's not really a name node per se, it's just maintaining a copy at all times of that edit log. So this is a little bit better than the previous situation where if you do need to restore from a failed name node, you can do so from an edit log that has a more up-to-date copy from your secondary name node and spin that up on your secondary name node. Another thing we should talk about is HDFS federation, and this isn't really about reliability so much as the ability to scale beyond a single name node. So remember we said that HDFS is really optimized for large files and not so much for lots and lots of small files. But you might find yourself in that situation where you do have lots and lots of small files, and eventually name nodes will reach their breaking point. There does come a point where a single name node just doesn't cut it. So HDFS federation allows you to say, okay, for these different subdirectories that we're going to call a namespace volume within our HDFS file structure, we can actually have separate name nodes that are responsible for each volume. And that way, a given volume will know which name node to talk to for reading and writing data files. So we can spread out the load of name nodes if we need to. So the relevance here to resilience is that if one of those name nodes went down, well, at least you only lose a portion of your data and not all of it, right? So you don't have to worry about restoring that given name node, which might not be quite as catastrophic as the entire HDFS cluster going down. Finally, if you cannot stand the possibility of some downtime on your cluster at all, there is something called HDFS high availability these days, and that is actually running a hot standby name node. The way it does that is by using a shared edit log. So your name node is actually writing to some shared storage that's stored in some reliable file system that's not HDFS. And that way, if your name node goes down, your hot backup name node can just take over right away. And it uses Zookeeper, which we mentioned briefly in our second lecture, to actually keep track of which name node is active at a given time. So your clients need to talk to Zookeeper in this configuration to figure out which name node should I be talking to for HDFS requests. and Zookeeper will say, okay, it's this one, and it will always make sure that every client is using the same name node at a given time. Now, there are complications here. This is a more complicated setup, and it has more complicated failure modes, as usually happens in this case. So there are ways of failing where you might actually have two name nodes running at the same time. And again, that can cause very bad things to happen because one name node might get a file write request and know about where that data is stored, and the other one might not. So if your read goes to a different name node, bad things will happen. So to protect against that, HDFS high availability actually goes to some extreme measures to make sure that only one name node is used at a time. And you can actually configure it to be so extreme as to actually physically cut off the power to a name node that it thinks is down. So when Zookeeper says, okay, I'm switching to this name node, it can actually cut the power to the other name node to make absolutely sure that no client is still talking to that name node. So it's pretty hardcore stuff, but obviously that takes a lot of configuration. All this stuff is really relevant more to Hadoop administrators than to you as an application developer or an analyst, but I just want you to know that the single name node isn't necessarily a big problem. There are ways of dealing with it such that it's not a single point of failure. So how do we use HDFS? Well, there's a few ways. One is just through a UI if you just want to copy files around and see where they are and sort of visualize the directory structure of HDFS. I mean, HDFS just looks like a big giant hard drive in this view, right? So it's distributed across many computers in a cluster, and it's highly resilient and available. But at the end of the day, it looks like a giant hard drive to you, with a file system. So, it's very easy to use from a client standpoint. There's also a command line interface that we're going to play with, and that's just, like using CD or whatever commands you might use on the command line, like ls or dir on Windows, but there are HDFS equivalents of all that, so we'll play around with that as well. You can also use HDFS through HTTP, and you can do that either directly or through proxy servers that sit between your HDFS machines and a client. So you can actually set up a web interface to HDFS as well. For most application development, or if you're going to be writing scripts on top of this data to analyze it, which is what we're going to be focusing on in most of this course, you'll be using the Java interface to HDFS. And Java doesn't mean that you're limited to programming in Java, because most other languages have ways of talking to Java code. So in that way, we can actually write code in C or Python or Scala or what have you. And under the hood, it can talk to the built-in Java interface of HDFS. Most of Hadoop, well, pretty much all of Hadoop is actually written in Java under the hood, so there's always going to be a Java client available for all these technologies. Finally, one other way of using HDFS is through an NFS gateway. NFS is a network file system, and if you are familiar with Linux, you've probably heard of it before, but it's basically a way of mounting a remote file system on a server. And the cool thing about that is that you can actually mount an HDFS cluster just like another server would be through NFS. So using the NFS gateway, you can mount HDFS to a Linux box, and it will just look like another mount point on your hard drive system, on your file system. So you can actually use programs potentially that don't even know about HDFS at all, because it will just look like another file on the file system to it using the NFS gateway. So that's pretty cool stuff too. But enough talk. Let's play. So as promised, let's go mess around with HDFS and see how it looks from a UI and also from the command line, and get some more hands-on knowledge of how it all works and how to use it. So let's get busy.